Hello, everyone. Good to see you once again. Today we have Paul Schemeil that's going to talk about the Kennison fundamental pro-sheaf and pro-group of a connected and locally connected locale. Thank you.
Hi everyone, thank you for being here today, and a special thank you to the organizers for this opportunity to share my work with you. So yeah, today we're going to talk about this Kennison fundamental pro-sheaf and pro-group of a connected and locally connected locale. So this was the topic of my master's dissertation, which was supervised by Martin Gallauer, and although it's not really a mainstream topic, nor it's what I'm currently working on in my PhD, I believe that there are some interesting aspects here that could be quite relevant for us in the context of homotopy theory. So let me begin this talk by, in a way, translating this title into English. And one way to translate it is a point-free approach to fundamental groups. And while this is the official title of the talk and it captures the essence of what we will discuss, I just want to offer another translation, a bit different, that might make the topic spirit and motivation a bit more clear, hopefully. So the translation I want to propose is the following. So the fundamental group of a pathological, but not too pathological space. That's better, hopefully, less obscure, but maybe still not very enlightening. So let me try to make more precise what I mean by pathological, but not too pathological in this context, hoping, to build enough motivation for the more technical part of the presentation that will follow. So let's begin by recalling what is the fundamental group. So as we know, the fundamental group of a pointed topological space is the group structure induced by the homotopy classes of loops at a base point. And this is a very interesting algebraic invariant, first introduced by Poincaré in 1895, and it encodes non-trivial information about the connectivity of a space. Again, as we know, for sufficiently nice topological spaces, the fundamental group has remarkable properties. The first one being the Seifert-Van Kampen theorem, which essentially states that the fundamental group of a space is locally determined. This means that if a space can be covered nicely, then the fundamental group of the entire space is completely determined by the fundamental group of the subspaces in this cover. And the second one is the well-known Galois correspondence. So there is a very strong relationship for, again, sufficiently nice spaces between the subgroups of the fundamental group and its covering spaces. But as for any algebraic invariant, the fundamental group comes with its own range of limitations. So the first one is that it's generally very hard to compute, especially in those instances where we cannot apply the Seifert-Van Kampen theorem. A second limitation is that it's not really a very fine invariant for high-dimensional spaces. For instance, one can show that for CW complexes, it only depends on the two skeleton. And now, a third and probably less discussed, let's say, limitation is that if a space lacks of sufficient path connectivity, then the fundamental group of such spaces isn't particularly insightful because the fundamental group fails to capture enough information about the space. And let me illustrate this with an example. So let X be a countable set equipped with the cofinite topology. Now this space is connected and locally connected since every non-empty open subset is connected, and this is because in this space with the cofinite topology, the intersection of any two non-empty open set is non-empty. But however, it's not path connected, and in fact, one can show that inside the space there are no non-trivial paths. This can be seen because if we assume that there was one, then this would give rise to a decomposition of the closed unit interval into countably many closed, proper, and disjoint subsets. And this can be achieved by simply taking the pre-images of points in X and then the union. However, such a decomposition of 0, 1 doesn't exist, and this is due to a result by Sierpinski. So in particular, f must be constant in these cases, and so the fundamental group of this space at each point is trivial. So this example illustrates that the lack of paths in a space limits the ability of the fundamental group to encode any significant information about the connectivity of the space. And for this reason, I will consider as pathological, but not too pathological, all the connected and locally connected spaces that are not path connected, or at least not necessarily. And this is because, as we saw in the example, for this class of spaces, the fundamental group doesn't seem to serve as a useful algebraic invariant. And from this perspective, the aim of my master's project can be briefly summarized in 2 points. So the first one was to study a more general notion of fundamental group, which was introduced by an American mathematician, John Kennison, in the paper, What is the Fundamental Group? And his notion of fundamental group can encode information about the connectivity of this pathological spaces without relying on the existence of the paths between the space. And the second goal was to investigate in these broader settings, and for this more general notion of fundamental group, the extent to which it's possible to recover standard results from the classical theory of fundamental groups, with a particular attention to the Seifert-Van Kampen theorem. Okay, so let's move on to discuss some intuition behind Kennison's notion of fundamental group. So while the details of the definition are a bit technical, the basic idea is actually very simple, and I would also say a bit elegant. And maybe you will agree with me, maybe not by the end of the talk, but yeah, let's go. So here's the picture. So if we have a path in a topological space, the thing is that we can in general approximate it by, hopefully you see the transitions, by a finite chain of overlapping connected open sets. And intuitively, the finer is this chain of open sets, and the more accurate will be the approximation of the paths. This makes sense, hopefully, yeah. So since, again, the path can be approximated in various ways, as we saw in this transition, we want to introduce, the first thing, we want to introduce relations that enable us to identify chains of overlapping connected open sets that approximate the same path. So the first thing is that, okay, so we want to, for sure, identify chains of the following type. So here in the picture, we have a chain, we have a path, and we have a chain A, B, C, D, and the chain A, lowercase b, C, D of open sets. And here, lowercase b is a subset of capital B. And we want to identify those. And to do this, we introduce the following terminology. So we are going to say that W is a simple refinement of a chain V if there exists an index I such that Wi is a subset of Vi. And for all other indices, they are equal. So Wj is equal to Vj. And in this case, we will also say that V is a coarsening of W. All right. Next, redundant extensions and reductions. So we want to be able to also identify chains that contain redundancies. We will say that a chain is redundant if it contains the same element in consecutive positions. And we will say that a chain W is a reduction of V if W can be obtained from V by removing a redundant element. And just to introduce even more terminology, I'm going to say that in these cases, V is a redundant extension of W. Okay, so the relation that we are going to impose on these chains, again, approximating paths, is the following. So we're going to say that V is equivalent to W if W can be obtained by applying this finite sequence of operations, so simple refinements, coarsenings, redundant extensions, and reductions to V. And this relation in some sense behaves as we expect, in the sense that approximations of the same paths are identified. For example, in this case, one can see that we can obtain the second chain from the first one by applying 4 redundant extensions by capital B, and then apply 4 simple refinements, since here these B1, B2, B3, and B4 are all subsets of B. So this chain gets identified. But now what it turns out is that this equivalence relation not only allows us to identify approximations of the same paths, but also approximation of homotopic paths. And to illustrate this and to provide some motivation, I will just go through another example. So suppose that we have a red path and a yellow path that are homotopic, and let A, B, C, D be a chain approximating the red path. And we ask, what is the effect of homotopy on this chain? And intuitively, we expect that this chain of open sets will be continuously translated, possibly with some deformation, to form a chain that approximates the orange path. And now the claim or question is whether it's possible to find a sequence of these simple refinements, coarsenings, and so on, in such a way that we can obtain this resulting chain from the original one. And in this particular case, one can show that it's pretty easy to see that this is possible. So starting from A, B, C, D, here I just used some colors possibly to make everything less confusing, or maybe more. But the first thing that we can do is apply 2 coarsenings by B union B prime and C union C prime, and then apply 2 simple refinements by B prime and C prime. But so the general idea that this example kind of illustrates is that the effect of homotopy on a chain can be viewed as a continuous deformation, as we said, of the open sets in this chain, in such a way that at each stage of the deformation, the resulting chain can be obtained by applying this finite sequence of operation to the original one. Let's consider like, what are we going to do with this thing? So now, given a space.
Before you continue, there's a question.
Okay.
Is there any requirements on the open sets A and B that they are connected or something?
Yeah. It is. Like at the beginning, I said we're gonna take approximations by connected open sets, and maybe later the relevance will be maybe more clear. But yeah, it is a requirement. Yeah.
And also,
if that was the question.
Yes, it was.
Yeah.
And another question: how do you formally define a chain? And how about paths which cannot be thickened by chains without them being self-intersecting?
I mean, a chain is essentially this finite sequence of connected open sets, such that, I mean, also their intersection is connected. And here I'm just providing, in some sense, an informal picture, and everything maybe later will be slightly more formal. But just to understand what is that we're trying to do, because of course we want to apply these in cases where we don't actually have paths, because this is more or less the object. Like we want to define this notion of fundamental group for spaces that are not necessarily path connected. So we want to use the sort of picture that we have in spaces that have paths to use these open sets to approximate these paths. Even if they are self-intersecting, it doesn't really matter. If you use a finer approximation, then the finer approximation will see the self-intersection. But if you use a very weak, in some sense, approximation, then this weak approximation will not see the self-intersection. But like right now, everything is more for motivation rather than being formal. But hopefully this answers the question. I don't know.
Yes, great, thank you.
Okay, no worries. Okay, so let's move on. So if we start from a space that is connected and locally connected, now instead of considering paths up to homotopy, we can study the data of chains of overlapping connected open sets that approximate paths up to homotopy. And with this, a natural approach to defining a sort of notion of fundamental group would be, okay, so we have a point P in a space X, and we look at a maybe sufficiently small neighborhood around this point, and we can study these chains from this neighborhood, which here is denoted by U, from U to U, and see what we get. So in fact, it's straightforward to check that this set together with the operation of concatenating homotopy classes of chains forms a group. And here the identity element will be the constant chain at U, and the homotopy inverse, let's say, is going to, of a chain of this form, is going to be given by U Vn dot V1 U. And here I'm just saying this, but it's not hard to check this. And intuitively, this seems like a good candidate for a generalized notion of fundamental group. However, with this naive and informal approach, there are some issues. And the first issue one may think about is that is this group independent of the choice of a connected open neighborhood around the base point? Because if, for example, we take a relatively large connected open neighborhood, we would expect that that would be different from taking a very small connected open neighborhood around the point. But actually, in this case, it turns out that the independence does hold. And the reason is that there is an even more serious issue with this approach. And the issue is that if X, the whole space, is connected, then any chain is actually homotopic to the constant chain. And the reason is that we can always find this chain of operations that reduce the original chain to the constant one. And here what I'm doing in this step is applying n times a coarsening by X. Then here I do some reductions, how many I need. Then here I do a simple refinement, and here I do another reduction. So in particular, this notion of fundamental group is extremely trivial. Okay. So before carrying on with more details on how this issue is resolved and outline, I think maybe it's a good point to stop if there are more questions about what I've said so far. But yeah, keep in mind that all the formal stuff is coming. So yeah, I'll just wait 30 seconds, otherwise I'll carry on. Okay, so let's go on. I mean, I don't know if there's anything in the chat, but I can't really see it. But yeah, maybe I'll just go. And in case there's any question, you can stop me. Okay, so as we pointed out, the issue with the so-called naive or natural approach is that when we approximate paths by chains of open sets, the larger are these open sets and the less accurate will be the approximation, and the less our homotopy relation is going to be able to distinguish these chains approximating paths. And again, intuitively, by what we said and by looking at the pictures, this makes sense, because the finer is the approximation, and the better it will approximate the paths. So this consideration hopefully motivates the idea that to encode more information about the space, we should approximate paths by gradually discarding the larger connected open sets and only allowing smaller open sets in our approximation. And this is essentially the idea behind Kennison's formal machinery. And to formalize this process of gradually discarding large connected open sets in a meaningful way, what we can introduce, and what Kennison did, is the notion of a connected base. Now, a connected base, the definition is roughly as follows. So a base of a space X is said to be connected if each element in this base is a connected open set. And moreover, we have this condition called the downward closure condition. So this means that if U is an element of our connected base and V is a subset of U, and V is also connected, then V belongs to our connected base. So this is the downward closure property. Okay, now if X is a space that is connected and locally connected, the collection of all possible connected bases of X, where here I denoted by CB of X, is non-empty, partially ordered by inclusion, and closed under intersection. It can be shown that the intersection of two connected bases is also connected. And moreover, the downward closure property ensures that when here mathcal W is contained in mathcal V properly, let's say, then every connected open set in V that is not in W can be thought as larger than W. And I mean, this becomes clear if you actually consider some examples, but also from the downward closure condition, I think it would make sense to say something like this. So now for each connected base of a space X, what we will do is essentially what we did before. So we will approximate paths in X, but now only allowing connected open sets in a specific connected base mathcal V. And the homotopy relation will be defined in the same way as we did before, but now only allowing simple refinements, coarsening, redundant extensions, and so on, of elements within the connected base V. And all these data defines for each connected base a groupoid, which we will denote by HV, whose objects are elements of the connected base V. And the morphisms between these connected elements are going to be V homotopy classes of V chains. And composition is again given as before by concatenation of these V homotopy classes of V chains. Okay, so now recalling the general idea from the naive approach, okay, what we will do is we will associate for any connected open set B in a connected base, the corresponding or the induced group, which here I denote by Young-HOM of HV from V to V. And moreover, when we have a connected element W, which is contained in V, there is a canonical group homomorphism from the two corresponding groups, which is given by conjugation by this chain WV. And it can be shown that this association is not only functorial, but it actually defines a sheaf on a base V of our space X. Hence, all these data can be encoded by the sheaf of groups that uniquely extends this sheaf on a base. And this is essentially the definition of a V fundamental sheaf of a space X. Okay, now we can do this for each connected base B. So we have that for each connected base, the information of all possible approximation of loops of V chains up to V homotopy is encoded by a sheaf of groups. And the idea behind the Kennison fundamental pro-sheaf is to essentially simultaneously encode all these data for each possible connected base of a space. So the Kennison fundamental pro-sheaf is, we can consider it as a purely formal object, which is defined as follows. So for each connected base mathcal V, we associate the corresponding V fundamental sheaf. And when a connected base W is contained in a connected base V, there is, and this can be shown that there is a canonical natural transformation between the corresponding fundamental sheaves, which essentially on objects are given as follows. So suppose that here alpha is a W chain, then we can map the W homotopy class of alpha to the corresponding V homotopy class of alpha. And notice that since alpha is a W chain, and it is automatically a V chain because W is contained in V. So, and also recall here I said co-filter diagram. So it's a pro-sheaf because the connected base of a connected and locally connected space, as I mentioned before, it's closed under intersection. So this is indeed a co-filter diagram. Okay, now before delving more into this notion of Kennison fundamental pro-sheaf and pro-group, I think it's a good point to spend a few words about locales. So up until now, I've made explicit that we are interested in developing a notion of fundamental group for the so-called pathological, but not too pathological spaces. And you may have noticed maybe that I've been a little bit reluctant to use the specific word topological space throughout the presentation. And this is because, as you might have noticed, the only data that we use to define the Kennison fundamental pro-sheaf and the V fundamental pro-sheaf is actually just the data of the open sets of a space. And for this reason, all this machinery can in fact be extended to locales. Now, locales are essentially generalized notion of spaces, which formally they are defined as a complete distributive lattice satisfying the infinite distributive law. And this is an algebraic object which effectively isolates the underlying structure of the open sets of a topological space. And they are called generalized in the sense that they are pointless. Pointless not because there is no point in studying them, obviously, but because in contrast to topological spaces, they do not automatically come with the notion of point, right? So in the context of locales, we can immediately extend all the notions of connectedness, local connectedness, basis, connected basis, since these notions are, even in the topological settings, defined just in terms of the open sets. So the V fundamental sheaves and the Kennison fundamental pro-sheaves of a connected and locally connected locale are well-defined notions, for connected and locally connected spaces are well-defined notions for connected and locally connected locales. Okay, so now let me just give a couple of concrete examples of concrete locales. So the first and probably the most immediate and natural example is the locale associated to a topological space. And this is defined as follows. So if we start from a topological space, we can look at the collection of all its open subsets, and the locale associated to X would be, yes, this as underlying set, the collection of all its open subsets, together with the induced sort of operations of taking arbitrary unions, finite intersections, and the inclusion relation. So you may notice that what we are doing in this process is forgetting just the data about points and just keeping the data of the structure of the open set of the topological space. And now you may reasonably ask whether any localic structure in some sense arises from a topological space. But this is not true. And if it was, locales wouldn't be generalized notions of spaces. And a classical example of this is the example of a pointless locale, so a locale without points. And this is the locale of surjections from the natural numbers to the real numbers. Of course, at the first glance, this might seem quite odd because, of course, there are no actual surjections from N to R. However, it is possible, and I will give in the next slide a construction, to define a non-trivial localic structure on this hypothetical space. And let me just go through that. So this hypothetical space, by definition, will be the locale that is generated by these elements U and X, so indexed by natural numbers and real numbers. And we want, in some sense, that these elements behave like if they were the open sets of surjective functions from the natural numbers to the real numbers, such that the evaluation of f at n is equal to x. So the next thing that we will do is to impose relations on these elements so that it is ensured that u and x actually behave as if it was the open set of surjective functions such that f of n is equal to x. And the relation that we will impose are three. So the first one is totality. This says that for each natural number n, essentially the union of over x in R of these open sets u and x is equal to 1. And what this relation aims to express is that for each natural number n, functions have some value at n. So explicitly, the union over R of the set of surjections such that f of n is equal to x for a fixed n is the set of all surjection, meaning that each surjection actually has a value at n. The second one is the functionality. So this says that for every natural number n and for any x and y distinct real numbers, the intersection of u and x and u and y is 0. So this relation kind of ensures that f is a function, because this simply means that there are no f's such that f of n is simultaneously equal to x and y. And the last relation is the surjectivity. So this says that for every real number x, the union over n of u and x is equal to 1. So this means that for each function f and each real number x, there exists a natural number n such that f of n is equal to x. So this is the construction, and the localic structure is highly non-trivial in the sense that these u and x, their behavior is not trivial. But however, it's a sort of hypothetical space, because actually there are no points inside of x. So the u and x behave as if there was a space of these surjections from n to R, but there's none. So this space is hypothetical. And now you may of course ask, but yeah, why should we care about this? Which might possibly serve as motivation. I don't know. So what I just wanted to say is that the one reason why people care about these locales is in the context of constructive topology. And one fundamental question in constructive topology, or in general in constructive mathematics, is how much topology or how much mathematics can we do without assuming the law of excluded middle or the axiom of choice? And it turns out that locale theory provides a framework where certain theorems, such as Tigonov's theorem, which you may recall, it just says that the product of compact set is compact, can actually prove constructively in the localic settings. And this is in contrast to the classical point set topology, where such constructive proofs are impossible to achieve. And in fact, Tigonov's theorem in point set topology depends on the axiom of choice. And again, here, beyond theoretical interest, this sort of approach of intuitionistic logic and constructive mathematics has become increasingly rare for real applications, for example, in proof assistance and formal verifications of AI-generated proofs. So the reason why constructive mathematics is kind of crucial in these areas is because it aligns with some computational methods, and it provides tools that are kind of compatible with the algorithmic language and processes. But yeah, I don't know much about that, so I'll just move on. And another thing that might interest someone is that this locale theory and this approach gives us tools to study these hypothetical or impossible structures, which might be interesting. But again, perhaps it's not better to get too philosophical, because these kind of things are relevant in philosophy, and we are homotopy theorists after all, and so let's go back to our object of interest. So recall that given a connected and locally connected locale, we have a well-defined notion of fundamental pro-sheaf, Kennison fundamental pro-sheaf. Now, given a point in A, we want to extract a group out of the Kennison fundamental pro-sheaf which encodes the approximation of loops at this base point. But now you may ask, what is a point in a locale? Because we said that locales forget the data of points and they keep only the information of the open sets. So how can we define points using just the data of the open sets? And in a topological space, I mean, to answer this, in a topological space, a point can be viewed as a continuous map from the one-point space to the whole space X. And this will induce, by just taking the pre-image, a map between the open sets of X and the open sets of the one-point space. And this is essentially all there is in the definition of a point in a locale. So if we denote by the symbol 2, the locale associated to the open sets of the one-point space, so essentially the two-element locale, a point in a locale can be viewed as a map from the locale to 2, which preserves the localic structure. Now, the more geometric, let's say, picture to have in mind is that a point is actually determined by an assignment of truth values 0 and 1 to each open set. Of course, a coherent assignment. But where 0 will denote the open sets that do not contain the point, and 1 will be the open sets where the point belongs. And this data is what effectively determines a point in a space. And I mean, the coherent assignment here is denoted by this preserving the localic structure. Okay, and this sort of picture also gives us a different sort of understanding of what it means to say that a locale is pointless. A locale is pointless if there are no such locale maps preserving the localic structure from the locale to 2. And so this is essentially all there is. So now, to define the Kennison fundamental pro-group of a connected and locally connected locale, we have A, our connected and locally connected locale, and a point P. The Kennison fundamental pro-group is going to be the pullback of our fundamental pro-sheaf along the point P. So this has a categorical description, but it can be checked that the result of this pullback can be we can give a more explicit description of this, and this is as follows. So for each connected base, we associate the corresponding group HOM HV from V to V, where V is any choice of an element in the connected base which contains the point, so such that P of V is equal to 1. And actually, up to isomorphism, it can be shown that it doesn't matter what specific V we choose. So all of these makes sense. And on transition maps, if W is a connected base contained in V, there is a canonical surjective group homomorphism from these two groups. Here I'm not describing the actual map, but there is one, and it's also canonical in the sense that it doesn't really depend on it depends on the choice of W and V, but there is a canonical way to find it, let's say. Okay, so this is all there is about the Kennison fundamental pro-group. And again, this is a purely formal object, but in contrast to the Kennison fundamental pro-sheaf, here the key observation is that these canonical group homomorphisms are surjective, and we can use a result due to Mordiek about the fact that if we have a formal cofilter diagram of groups where the transition maps are surjective, then this data is an actual cofilter limit of discrete locale groups. Locale group is this locale group is a group with the sort of discrete topology on it. Let's say it's a group object in the category of locales. But so what you have to know is that this is an actual, it's not just a purely formal object, but it's an actual locale group. And the main result from Kennison that Kennison showed is that if locale A corresponds to, so it's the locale associated to a sufficiently nice topological space where, I mean, here nice means being connected, locally connected, and if I remember well, admitting universal cover. But if it's sufficiently nice, then this notion, his notion, Kennison fundamental pro-group, actually recovers the usual topological fundamental group. And it recovers it without relying on the existence of paths, because its definition just uses the open sets. And this result is what motivated me, like in my master's project, to investigate generalizations of certain results in the classical theory of the fundamental group, and specifically the Seifert-Van Kampen theorem. Now, in this last part of the talk, I just want to give a brief overview of my attempt, which I did in my dissertation, but I will just sketch some, the main ideas. So first, let's recall the statement of the Seifert-Van Kampen theorem for the classical fundamental group. So this states that if X is a topological space and U and V are open path connected subspaces that cover X and have non-empty and path-connected intersection, then for any choice of base point in U intersect V, the following diagram is a push out in groups. Objective for us is to generalize these assumptions in the context of connected and locally connected locales, and this can be done as follows. So first, instead of starting with a topological space, we will start with a connected and locally connected locale, since our notion of Kennison fundamental progroup is well defined for this object. Then the topological assumption of having two path-connected open subspaces that cover X can be translated to the assumption that we have two elements. Instead of saying path-connected, because I will say something more later, I will just say having two open subsets of X which cover X is translated to the assumption of having U and V in the locale A such that their union, or the symbol means join, which behaves as a union, is one. So is the whole space. And the assumption of U, V, and their intersection being path connected can be translated to the assumptions that the locale generated by U, V, and their intersections are connected and locally connected. This symbol, down arrow U, just means that it's the locale associated to essentially the subspace U. So concretely, essentially this as a set is the collection of all A in A such that A is less than or equal to U. And the localic structure on this collection is induced by A, in the same way that the topology on U subset of X is induced by the subspace topology. Okay. And finally, having a point in the intersection is the same as having a point in the locale generated by the intersection. So with this assumption, the conjecture that we propose is that the corresponding diagram, here I'm not telling you anything about the maps, but there are some maps which can be described. But the assumption, the sort of conjecture that we propose is that under this assumption, this diagram is a push out of progroups. And this conjecture seems to be plausible, at least for a sufficiently nice locale, since, as we've seen in those cases, if the locale is associated to a sufficiently nice topological space, our Kennison fundamental progroup recovers the standard topological fundamental group. So we would expect that for nice cases, this thing can be proved. But while it's not clear, at least to me, if the conjecture holds in its full generality, we were able to establish some intermediate results with my supervisor, Martin, and a partial proof of the conjecture for specific cases. Now, let me just say something about this. So first, I just want to give you the first key intermediate result that was useful to give a partial proof of the conjecture, and this as follows. So first, let me fix some notations. Now we are working under the assumptions that we've established before. So if we have a connected base V, we can consider the corresponding connected bases of the locales generated by this U, V, and U intersection V. explicitly these connected bases are given by like the whole connected base intersect with for example this locale, and it can be shown that this is it's actually a connected base for down arrow u. Okay, so all of this makes sense. And the intermediate result is that if we start from a connected element in the connected base restricted to the intersection, and moreover, the connected base satisfies this assumption so that it can be written as the union of VU and VV, then the following diagram is actually a push out in groups. If we have some extra time later, and also depending on your questions and interest, I have a sketch of the proof of this argument that I can discuss. And in general, the details also, as we will see, the actual details are a bit technical, but there are a few ideas that are kind of inspired by the topological proof of the Seifert-Van Kampen theorem. But I mean, okay, so having said that, after proving this key intermediate result, what we were able to identify are like some sufficient conditions on how U and V actually cover the locale A. So sufficient condition that made it possible to reduce the proof of the whole conjecture to essentially this property. And while, I mean, our additional conditions of, I mean, being well covered is quite weak, so it holds for many locales. There are also many examples where the locale does not admit such a coverage. And in these cases, like for these cases, the natural question to pose is, okay, so maybe we might find a counterexample for all these cases. And we tried, but the major obstacle that we've kind of encountered is that it's extremely hard and challenging to actually compute the Kennison fundamental pro-group of a general locale. And in my opinion, this remains the sort of main limitation, which is an important limitation in the context of homotopy theory and algebraic topology. So it's the main limitation for this object. And let me just give a couple of points as for like what are exactly these computational difficulties. So the first one is that in general, understanding these groups is very hard. And this is because deciding whether two V chains are V homotopic. So this means finding a finite chains of operations which transforms one chain to the other. It's always a combinatorial problem. So in specific examples, one can find the correct trick that works. But in general, it's very difficult to handle. And so this is the first problem. And the second one is that even if we have an understanding of these groups, the collection of all possible connected bases of a space or of a locale is very large. And it's in general quite unclear how to, actually list, for example, all the possible connected bases, or if it's not necessary, because at some point we will compute a co-filtered limit. It's also unclear, I mean, how to deal with the data, like where do we find the correct connected bases that contain the actual information that we require. So with these challenges, there are several avenues for further research that kind of present themselves. The first one is, of course, prove or disprove the Seifert-Van Kampen conjecture in its generality. And the second one, which is related to the first one, is to, I would say, develop more sophisticated tools to actually compute the Kennison fundamental pro-sheaf and group. And I mean, I think this is sort of needed if one tries to look for counterexamples for the Seifert-Van Kampen theorem, as I mentioned before. And the last one, which is a more theoretical sort of direction with a little, I would say, a little literature, is to develop a notion of homotopy equivalence in the context of locales that can possibly generalize appropriately the notion of homotopy equivalence in topological spaces. And what is interesting is that if one can appropriately define such a notion, then how this definition of Kennison fundamental progroup could serve as an invariant under this notion of homotopy equivalence, and this would like make it possible to classify and to study and classify locales up to homotopy equivalence and explore the extent of various results in algebraic topology in this localic framework. So this concludes my presentation. If there are any questions, I'm happy to start a discussion. Otherwise, here, I mean, I have an extra section, but I will go through that only if you're interested, because there are, I mean, also some boring details over there. So yeah, for now, thank you.
Thank you very much.
Thank you.